In this lecture, we're going to do a quick review of linear equations, including looking at some situations where equations that don't look linear at first can be turned into linear On this slide, I have an example of what looks like a rational equation. Well, actually, it is a rational equation. And it definitely doesn't look like a linear equation because of all the variables in the denominators. However, let's see what happens when we start solving this. The first thing I need to do is factor all of the denominators. Now, the first two can't be factored any further, but the last one factors to x times x plus 1. Now, to solve the equation, I'll start by multiplying through by the denominators to eliminate them. I'll start by multiplying both sides of the equation by x. Now, on the left side, the x's cancel, leaving me with just 2. And on the right side, when I distribute the x to both of the terms inside the parentheses, the x's cancel on this right-hand term, leaving me with 4 over x plus 1. And on the second term, there's nothing to cancel here, so I'll just leave the x multiplied by the numerator. Now, to eliminate the remaining denominator, I'll multiply both sides of the equation by x plus 1. That's going to cancel the x plus 1's on the right-hand side, leaving me with 7x minus 4. And the left-hand side will become 2 times x plus 1. Now look at what's happened here. I've gotten rid of the denominators, and I don't have any exponents. So I've converted the original equation into a linear equation that I can solve using our standard linear equation solving procedures. I'll start by distributing the 2 into the parentheses on the left. Then I'll subtract 2 from both sides. Then I'll subtract 7x from both sides. And finally, I'll divide both sides by -5 to get the final answer. X equals 6/5. In the last several slides, I want to look at some practical examples of how linear equations are used in a number of different settings. Now, on this slide, I have an example of a situation where they would be used in HR, or human resource management. A common situation in sales organizations is for employees to get a base salary that's usually fairly low and a commission on their monthly sales. The idea here is to tie employees' salaries to how much revenue they bring in for the company. So the question here is, how can we convert this payroll situation into an equation that we can use to calculate the salaries of individual employees every month? So to do that, I'm going to use the base equation that I have here. The employee's total salary is equal to the sum of their base salary plus their commission. So I already know that the base salary at this company is $1,200. And to get the commission part, I'll let S be the monthly sales of an employee. Now their commission is going to be 5% of that, or 0.05 S. Now if I replace the total salary with, say, P for payroll, I'll have the equation that I need. And notice that this is an example of a linear equation, an equation that could actually be used in a business environment. For example, if you knew that an employee's monthly sales were $1,000, then you could replace the S here with 1,000 and then simplify the right-hand side here to get their actual payroll, the actual salary that they would get paid that month. Now, on this next slide, I set up an example of how this calculation could be implemented, say by a payroll processor in a small business who might be doing these calculations in a spreadsheet program like Excel. The processor could list all of the company's employees in column A, their monthly sales in column B, and the formula that I have here in column C would automatically calculate their monthly paycheck amount. On this slide, I have an example from physics that could be used in a manufacturing operation. The specific heat of a substance is the amount of energy needed to raise the temperature of 1 unit of mass, usually a gram, by 1 degree Celsius. Now, at first, this may not look like a linear equation that we've talked about so far because it has too many variables. There's Q for the heat required to raise M units of something with a specific heat of C by T degrees Celsius. However, in a manufacturing setting, you're going to know what kind of material you're trying to heat or melt, and that's going to determine the value of C in the equation. For example, the specific heat of water is 4.186 joules per gram degrees Celsius. So if I substitute that into our equation, it becomes Q equals 4.186 MT. Now, you're also going to know the amount of the substance that you're trying to heat, and that's the M in the equation. For example, you may be working with containers that hold 100 kilograms of water. Now, 100 kilograms is 100,000 grams. So if I substitute that for the value of M in our equation, it becomes Q equals 4.186 times 100,000 times T, or just Q equals 4,186,000 T. Now I have something that looks like a linear equation in two variables. This is something that the production foreman could use to determine how much energy it will take to heat the water to a specific temperature T. And based on this, he can tell how long the process will take based on the amount of heat his heating units can produce. So doing this kind of time calculation is going to be an essential part of setting up a manufacturing production line where one step has to be completed before the next one can start. Now, I have one last example here that comes from a sales situation. This is a question that I actually got asked while working at a local martial arts school. The owner didn't want to have to make change for selling bottles of water, so he wanted the final price that the customer had to pay to be exactly $1. And what we needed to know was what number should be entered into the cash register so that after the sales tax was added, the final cost was $1. So to answer that question, we need this general equation that I have here. The final cost is equal to the list price plus the sales tax. Now, the list price is what I'm trying to find, so I'll replace that with a variable, X. And I know what I want the final cost to be. That's going to be $1. Now that leaves me with the sales tax. Calculating the sales tax, you would multiply the list price by 7%. But the list price is our variable X, remember. So the sales tax part will be 0.07 times X. So now look at what I ended up with here. This is just a linear equation. If I add together the two terms on the left-hand side, the equation becomes 1.0x. And if I divide both sides by 1.07, I get that the list price of the item, the amount that should be entered into the register, is 1 divided by 1.07, or 93 cents.